In this video, we discuss learning outcome number 2 for lesson 5.1, which is all about probability distributions. Here's the definition. A probability distribution gives the probability for each value of a random variable. It can be expressed in a number of different ways. You might see it in the form of a table. We could express it using a formula, or we could express it using a graph called a probability histogram. Probability distributions also have to satisfy 3 conditions, which we'll talk about next. So here are the conditions. First of all, there must be a random variable x. Now remember, random variables are numerical, not categorical. So if you see categories in a table, you know you're not looking at a probability distribution. Now, associated with each value of that random variable, we have to have a corresponding probability. Next, the sum of the probabilities needs to equal 1 when x assumes all possible values. Now, you might get something like 0.999 or 1.001 when you add up all the probabilities in the table. That's completely fine. Those differences from 1 result from rounding errors, and they have nothing to do with the probabilities themselves. Now, if we were to use numbers that were exact, so we're not estimating at all, the sum of all probabilities should still be 1. Just the numbers in the table may not capture that because we have to round to write the numbers in the table. Now, for every x value, so that's every value of our random variable, the probability has to be between 0 and 1 inclusive, otherwise it's not a probability. Now, when you're looking at these tables, you might see something like 0 plus listed in that probability column. If you're wondering what that is, this slide will tell you what that's about. This represents a probability value that's positive, but it's very small. For example, if you have 0.0000000000125, that is a tiny probability. If that is a probability of some event, that event is very unlikely to happen. But it doesn't have a probability of 0. It could still happen. It's just very unlikely. So we use this 0 plus in the table whenever we want to indicate a probability that is so small that we would typically round it to 0, but it's not 0. We want to make sure that we don't round to 0, because if we round to 0, that would imply that the corresponding event is impossible, when the reality is that it's just extremely unlikely to happen because the probability is so close to 0. Now here is an example. This is something like what you might see in your homework. It says 5 males with an X-linked genetic disorder have 1 child each. The random variable is the number of children among the 5 who inherit the X-linked genetic disorder. So they have 5 children, and you're asking yourself, well, how many of those children inherited the disorder? It might be the case that no children inherit the disorder, 1 of the 5, 2 of the 5, 3 of the 5, all the way up to 5 of the 5. And each of those would be associated with a corresponding probability. And that's what this table seems to show us over here to the right. The question says, determine whether the table represents a probability distribution, and then determine whether X is a discrete random variable or a continuous random variable. Now let's check our conditions. First, you have to look at those X values. Do we have a numerical random variable X? We sure do. And its values are associated with probabilities. Now, if we add up all the probabilities in this table, we get 1. Now, that's not 100% obvious, but if you get your calculator out and you do the arithmetic, 0.031 plus 0.156 plus 0.313 plus 0.313 plus 0.156 plus 0.031. I think I said 516 before, I meant 156. But I don't know if you guys can see it. That's 1. It's 1. There we go. So the sum of the probabilities is 1. And then remember what that last condition is. All the values in that probability column have to be between 0 and 1 inclusive, and they are. So this is a probability distribution. Oh, forgot to answer that question about the variable X. Is it a discrete random variable or a continuous random variable? Well, X takes on 6 possible values, 0, 1, 2, 3, 4, and 5. 6 values. That's a finite number of values. Since that's a finite number of values, that's definitely a discrete random variable rather than a continuous random variable. Now we can also visualize probability distributions through probability histograms. This is just another way to express that probability distribution. It's just like a relative frequency histogram with one difference. Rather than having frequencies on that vertical column or relative frequencies in the vertical column, we have probabilities in the vertical column. Now, each probability is associated with a value of that random variable x. The values of the random variable x are listed on the horizontal axis, and then this is what we see. So here's a probability distribution in the form of a table for the number of heads that you get when you toss a coin twice. Now remember what the sample space was. You could get heads and then heads. You could get tails and then tails, or you could get a head and then a tail, or a tail and then a head. So the chance of getting no heads, that's 2 tails. That's 1 out of 4 possibilities. So that has a probability of 0.25. The probability of getting 1 head, well, it's 2 out of 5 because you could have a head and then a tail, or a tail and then a head. So it's 2. I said 2 out of 5. I meant 2 out of 4. 2 out of 4, and 2 out of 4 reduces to 1/2, or 0.5. And then finally, the possibility or the probability that you could get 2 heads is 1 out of 4, which is 0.25. Now we can represent that graphically like this. Now notice this over here, that because each value of the random variable is just an integer. So this is a value of 0, and this is a value of 1, and this is a value of 2. If we make those bars in this histogram 1 unit wide, then the area of each of these rectangles corresponds to the probability, because it's just the probability tall by 1 wide. So I'll take 1 and I'll multiply by the probability, and I get the probability. So this area is 0.5. This area for the rectangle on the right is 0.25, and this area is 0.25. If we add all of those areas together, we get 1, which is the same as summing up all of the probabilities. We're going to see this correspondence between area and probability again when we get to chapter 6. So keep that in mind, that if we have these values of the random variable down here, and those values of the random variable are just integers, like we have 0, 1, and 2, for example. If we make those bars 1 unit wide to represent, well, just the difference between 2 integers, then the height of that bar represents the probability, but not just the height, the area of the bar represents the probability, because we're taking that probability and we're multiplying it by 1 when we do length times width to find area. So area is associated with probability here, and we'll see that again in chapter 6. Now, we also said that probability distributions can be described with formulas. Now, this one is not 100% obvious, not at all obvious. I don't know why I said 100% obvious. It's not at all obvious, but probabilities can often be described this way. So here is the formula for the number of heads that you can get in 2 coin tosses. So the probability of x, that's x heads, turns out to be 1 over 2 times 2 minus x factorial times x factorial, where x can take on the values 0, 1, and 2. If you're saying to yourself, how on earth does that give us what it's supposed to give us? Let me show you my paper, and we'll evaluate it, and we'll see that we get exactly the same thing. Okay, so here is the probability formula for the probabilities associated with getting x heads when you toss the coin, twice. So you could have 0 heads or 1 head or 2 heads, and this is going to give you the associated probability. Now, as I said, it's not at all obvious. If x equals 0, let's see what we get. We've got 2 times 2 factorial times 0 factorial. And remember, 0 factorial is defined to be 1. So this is 2 times 1, which is 1 in 4. So there's a 1 in 4 chance that you would get 0 heads. And remember what our sample space looks like. You can have heads and then heads, heads and then tails, tails and then heads, or tails and then tails. Well, there's a 1 in 4 chance that that happens. So that formula gives you that. You might say, really? Yes, really. Now, if I plug in x equals 1, so that's the probability of getting 1 head from here, we have 2 times 2 minus 1 factorial times 1 factorial. 2 minus 1 is 1. So that's 1 over 2 times 1, which is 1/2. And there are 2 out of 4 options in that sample space that will give you 1 head. So the probability is 1/2. And then let's see what happens when x equals 2. So that's 2 heads. There's a 1 in 4 chance there. We know that that's the answer. Well, here I've got 2 minus 2 factorial. That's 0 factorial, which is defined to be 1. And then 2 factorial over here is just 2 times 1. So we get 1/4, 1 out of 4. Now, if you're saying to yourself, how did they get that formula? We're going to talk about that when we talk about binomial distributions, in the next lesson when we talk about 5.1. So if you're curious where this came from, we'll talk about it. We'll talk about it very shortly. Now let's go back to the PowerPoint. So we can describe probabilities with formulas as we did right here. We see that when we substitute x equals 0, 1, and 2, we get these probabilities. So it's the exact same answer. Now let's look at one more example. This is dealing with job interview mistakes. The problem statement says, hiring managers were asked to identify the biggest mistakes that job applicants make during a job interview. And the table to the right is based on their responses. And this is based on data from a particular survey. The question says, does the table describe a probability distribution? Well, X is inappropriate attire, being late, lack of eye contact, checking a phone, or texting. And then it's associated with a probability. I don't think this is a probability distribution. Remember, you have to check those 3 conditions. The first condition is that X is a random variable, which means it's numerical. And this is categorical data. This is not numerical data. So this is not a probability distribution. Another condition that fails to hold is that the sum of the probabilities is supposed to be 1. And if we add 0.5 and 0.44 and 0.33 and 0.30, we get 1.57. So there's something a little fishy about these numbers. We might ask for more clarification about how these numbers were calculated and what they truly represent. So this is not a probability distribution. Since all 3 conditions are not satisfied, the table does not describe a probability distribution. It might give you some good information, but in order to understand that information, in order to read this and make sense of it, we'd have to know what they mean by this 0.5 over here, or this 0.44, or this 0.33, or this 0.30. Now, we could spend a little bit of time thinking about it, but we've already answered the question, so I think we'll move on from here. Now, that is it for our study of probability distributions. Next, we will talk about finding the mean, variance, and standard deviation given a probability distribution.